So let me introduce quickly eMotor Director. Welcome everyone. And as Simon introduced, this is a tool that is dedicated to the multiphysics optimization of eMotors. When designing electric machines, you need to consider various physics and like thermal, efficiency, torques, power, stress, noise, impact of PWM. So all those physics, you have some constraints coming from those. And if you are able to take into account all those constraints in a single optimization loop, this is a lot of time you can gain. But such optimizations are not so easy to set up. It usually requires quite a lot of manual work with parameterization, model setup, linking all models together, managing the parameters, the models, the data. And that's why we have created eMotor Director to automate this kind of multiphysics optimization of eMotors and giving a platform that simplifies and speeds up the setup of such studies. It will really allow to run complex optimization studies, considering multiple physics, but also having interactions between 1D and 2D or 1D and 3D. You will see from Abdesamed demo after my presentation. Considering also multiple working points, considering multiple concepts, and even giving the possibility to do motor family optimization. So I will illustrate those points in my presentation. And really the platform, what it will help you to do is really to manage all your projects, models, data, and parameters in an easy way. So what is the process you need to follow as a user when using eMotor Director? The first thing you will do is to define the motor you want to optimize. So you have a baseline design, which is based on a flux motor template, but you can also bring your own design, a parametric design. And you will define all the parameters first and your geometry, and then you will define all the different physics that you want to consider. So defining the simulation process, so EM calculation, thermal calculation, everything that you want to consider. And in fact, what it will do is that we will run DOEs, and those DOEs will build the relation between the outputs you have defined and the parameters that have been considered as inputs. And thanks to these DOEs, we will be able to generate meta models that are the base for the optimization. So we are really running here indirect optimization so that we can speed up the optimization process. So you define your objectives, your constraints, and the optimizer will find a global optimum based on those response surfaces. And in the end, you will verify on using the finite element model that the results you have obtained. So this is a general workflow of the tool. And usually in most people, when doing such multiphysics optimization, just limit themselves to a single concept. And in the tool, you can extend to multiple concepts. So we generate DOEs for each concept. So here we see I have displayed 3 concepts, one with delta shape here. Here we have 2 layers. Here we have 3 layers. And we will create all those DOEs on all concepts, and this will create a database of results that will be used to run the optimization process. And the optimization algorithm will pick the best solution out of all the concepts that are considered. Okay. So let's see now on an example how it goes in the tool. So I'm taking here the example of Saietta, who has used this as a platform for the design of an electric motor for a traction application. I won't go too much into the details, but just to give you a flavor of how it goes. So here we have two geometries considered, one with 8 poles, 12 slots, and the other one with 12 poles, 18 slots. And on the top of it, we are also considering different gear ratios. So 2 gear ratios, in fact, are considered in the study. So you see, you have multiple configurations that are considered in the optimization process. Show you a bit also what are the inputs and outputs that are considered in the study. So here we have the design variables. And here you have the different responses that we want to constrain or we want to optimize. So looking at peak power, peak torque, we have also short circuit current, demagnetization, we have temperatures, rotor stress, cogging torque and torque ripples. And here we are minimizing a cost function. Okay. And on the right here, you have all the different physics. So each line is a different computation, and that will just compute the outputs that are necessary to be evaluated for the constraints and for the cost and for the objective. Okay, and the objective being the cost here. So let's go through a short video showing how it goes into the tool. So here in the middle, you see your geometry with the parameters. On the left here, you have a library of studies that you can pick and choose, and you just drag and drop them, and you will define dynamically here on the screen, just using those boxes and arrows, the various physics you want to consider. You can link various physics together. For example, if you want NVH, you need first to compute the forces, which is an EM computation, and then you send the forces to NVH. And for temperatures, you need to compute the losses first, and then send this to the thermal computation. After you define the physics, then we have a special screen here to define all the design variables that you want to consider into your DOEs and optimization with lower bounds and upper bounds. Then we go to responses. So all the output values that you want to consider in your study. So you just select among a list of values that are available, and very easily then you will be able to constrain them in the optimization. But let's run the DOE first. So just click on run, and then we'll be able to distribute all those computation over several cores or several machines to speed up the evaluation of the DOEs. So this is what we are doing here. And when it's running, then you have a dashboard that is showing you the progress of the DOE execution. Just in real time, you see the execution and you can check if everything goes well. Once this is done, then you have your DOEs executed, you have your response surfaces that are available, and then you can just define now your optimization. So what I had in my PPT, now I'm just entering all those values inside the software. So inputting the constraints and also defining the objective function. Once this is done, you just need to let the optimization go, and you will be proposed then the best solution, the best feasible solution it has been able to find during the optimization process. in the end, for this particular study, we had 4 good candidates here that are from left to right. We go from the maybe the most efficient, but also the most expensive. And on the right, we have less efficient, but also with lower cost. Then, let's say the designer then needs to make the choice, the best choice for his application. So this is what Saietta has done, and this was like a multi-concept optimization that is there. And then for motor family optimization, so here we are in a story where you don't optimize only one motor, but a family of motors. So you have 3 levels of power, and you want to reuse like common stator part or common magnets. Then you need to find the good compromise between the number of common parts and the efficiency of your solution. And this is typically what ZF is using eMotor Director for, is to find this good compromise between the number of common parts and the efficiency of each motor in the family. We see here on the graph on the right that the more common parts you have, and the more sacrifice you need to do on the energy consumption. So it's really a trade-off study that you can do thanks to that. So I'm done on my side, and I will let now Abdesamed continue and illustrate how EMD can be used to consider in the process PWM control and NVH.